Okay. So today we are going to solve 8th assignment of previous year. So in this particular assignment we are mainly going to deal with coherent states. So I thought I'll talk about what these coherent states are before we begin solving the assignment. Okay, so what are the coherent states? Coherent states are nothing but eigenstates of the annihilation operator. So in the harmonic oscillator potential, to solve the spectrum of the harmonic oscillator potential, we introduced two operators which are not Hermitian. Where A is square root omega, so where A is x over h cross 2h cross over m omega plus I p over square root of 2h cross m omega, and A dagger is minus I. So A and A dagger are not Hermitian operators, and their eigenvalues can in general be complex. And what are the coherent states? So coherent state is the eigenstate of annihilation operator. Okay. So you all know this, but I'm just recapping. So coherent states are eigenstates of the annihilation operator. So this is annihilation operator. Because if we are in n particle state, A acting on that state takes us to n minus 1 state, that is to a state where there are n minus 1 particles. That's why we call it annihilation operator, and A dagger is the creation operator. So we express the coherent state as alpha. A acting on alpha gives eigenvalue alpha and that state back. Okay. Now, what are the form of these coherent states? I mean, what do they look like? So any state we can write as a superposition of the basis states. Right? Now in harmonic oscillator, what are the basis states? So the states of the eigenstates of the number operator or the eigenstates of the Hamiltonian itself forms a basis. So these coherent states we can express as a superposition of those basis states. So in some coefficient dn and then those basis states. So these are nothing but eigenstates of the number operator, also the eigenstates of the Hamiltonian. So number operator, which is defined as A dagger A, that number operator acting on n gives n as eigenvalue, and Hamiltonian gives h cross omega n plus 1. So they form a basis. So that's why this coherent state we can express as a linear superposition of those basis states. Now we want to determine what these coefficients are. So in order to do that, what can we do? We can first we can evaluate this left hand side as well as then substitute this alpha on the right hand side and then compare both sides to figure out what these coefficients are. So what I mean is, A operating on alpha will, so this is what? This is actually D0 0 kit plus D1 1 kit plus and so on. So what A acting on n particle state gives square root n minus 1. So that is what we need to apply for all these number states. So D0, so when A will act on 0 kit, it will give 0, right? Because it's 0 square root 0 and then you can't have minus 1 state. So I mean, this is the basic property that annihilation operator acting on the ground state gives 0. So the first term vanishes and from the second term we get D1 square root 1 and then 1 minus 0 meaning 0 kit plus D2 square root 2 1 plus D3 square root 3 2 and so on. Okay, so this is your left hand side of this eigenvalue equation. And right hand side is alpha on alpha and alpha on alpha kit, I mean, and that is what? That is D0 0 plus D1 1 plus and so on. Now if we equate these two, because that is the because alpha is eigenstate of A, so we equate these two. So let me comparing 1 and 2, we can determine the coefficients. So what do we get? D0 is nothing but D1 is equal to D1. Then D2 square root 2 is D1. So square root 2 is equal to so D2 square root 2 is again D1, but D1 is D0. So we obtain D2 to be D0 over square root 2. Okay, and third term will give us D3 square root 3 and that is equal to D2, and D2 is what? D2 is D0 over square root 2. So this implies D3 is D0 over square root 3 times 2. So we can see the pattern Dn will be D0 over square root n factorial. Is that clear? So what does that mean? Alpha kit, the coherent state, is basically summation over n. Dn is D0 over square root n factorial n. Okay. Now, okay. Now,
Madam,
yeah.
can you please explain once again?
So, so this portion you have difficulty in understanding.
Yes, madam.
So what are we doing here? We are trying to find out what are the coherent states, and coherent states are, the definition of coherent state is that they are eigenstates of the annihilation operator. Okay, so we start with this equation that annihilation operator acting on the coherent state is giving you eigenvalue alpha and then that state. Now we want to determine what these coherent states look like in terms of our known eigenstates of the Hamiltonian of the problem. So this is the Hamiltonian of harmonic oscillator. I mean, this is not the Hamiltonian, this is, oh sorry, I forgot to write the half, n plus half h cross omega. So Hamiltonian is h cross omega a dagger a plus half. So we know the eigenstates of this Hamiltonian, and those are this state n, kate n, and so since they are eigenstates of the Hamiltonian, they will form a basis, and we know any state we can write as a linear combination of the basis states. So this is what we start with, and then these are unknown, and we substitute this alpha on this equation and then try to figure out what these coefficients are. Okay, now n starts from 0, goes up to infinity. So alpha, the ansatz that we are taking is this, and that can be written in this way. I mean, if I just so n starts from 0 and goes with integer steps, so d0 0, d1 1 and so on, and this particular state we replace in this equation. So and then act with a on alpha and equate it to alpha kate. That's what we are doing here. In equation 1 is a acting on this state alpha, and a acting on alpha, what would it give you? So a acting on any kate n gives you square root n minus 1. This you know. So
Yes, madam.
so okay, so then what will you get? So when a acts on 0, it gives 0 because that's the ground state. It cannot you cannot get any state below the ground state. That's the lowest energy state. So a acting on 0 gives 0, and then d1, a acting on 1 will give you 0 kate, a acting on 2 will give you square root 2 1 kate, and so on. And from the right hand side you have alpha times the state. So alpha times the state, I missed the alpha. So this is the state alpha kate, and then that is multiplied by the coefficient that is multiplied by this eigenvalue alpha. So basically alpha d0 is d1, which, or I can write it as d1 is equal to alpha times d0, and yeah, so okay, now from this we will get d2 square root 2. d2 square root 2 is equal to actually alpha times d1. I apologize for the mistake. So alpha times d1, and d1 is alpha d0, so you get alpha square d0. So from there d2 is divided by alpha square root 2. Am I making any mistake? Alpha square d0, so okay, sorry, yeah, alpha square is in the numerator, right? So alpha square d0 over square root 2. Likewise, if you compare these two, if you compare now this and this, so you get alpha d2, and d2 is alpha square d0, so alpha times d2 will be alpha cube d0. So d3 is alpha cube d0 over, and so dn is what? Dn is d0 alpha to the power n over square root n factorial. Do you understand now what is happening here? We are not doing anything except that we are just replacing this state which we have written as a linear superposition of our linear superposition of the eigenstates of the number operator, that we are replacing here, and then trying to figure out what these coefficients are by comparing left hand side and right hand side. Is this clear to you? Otherwise I'll
Yes.
explain again.
Yes, madam.
Okay, now we have this particular form of our coherent state now, but this is not enough because d0 is still unknown to us. So there is normalization property. These coherent states should be normalized. So we expect the inner product of the state with itself to be 1, and if we demand that, we will be able to figure out what this d0 is. So let's do that. So this is the kth vector. The dual vector will be, let's use a different dummy variable, d0 star. Now alpha star. Why am I doing alpha star? Because remember, these annihilation operators are not Hermitian. So if you do a cap dagger, you will not get back a. Okay. So a dagger and a are two different operators. So they are not Hermitian. So what does that mean? If it is not Hermitian, their eigenvalues are not real. They can in general be complex. So when I write down the dual vector from this kth vector, I need to do star of the eigenvalue because they are in general complex. Okay. Now so what do we get for the inner product? Summation over n m, both runs from 0 up to infinity, d0 mod square alpha to the power n alpha star to the power m square root of n factorial m factorial. Okay. Inner product mn, that is equal to 1. Now what is this? These base states are all orthonormalized, so this has to be delta m comma n, and if you take summation over m, let's say, then all m has to be replaced by n. That's what the property of delta function says. So delta n comma m is equal to 1 if n equal to m, and 0 if n not equal to m. So we get summation over n. Suppose we are taking the summation over m here, so summation over n remains d0 mod square. Now alpha to the power n, alpha star to the power n will give us mod of alpha square whole to the power n. Okay. Now square root n factorial square I'll get, so we can write it as n factorial, that is equal to 1. Okay. Now what is this? So what is this entire thing? That is nothing but exponential. So exponential of x you can write as summation n equal to 0 to infinity x to the power n over n factorial. So what is x for this particular case? X is mod of alpha square. So we get mod d0 square times exponential of mod alpha square, and that is 1. So we can determine d0. So we do it on next page. So d0 is exponential minus mod of alpha square over 2. Okay, so this is how we determine what d0 is. Now alpha ket is known to us.
Madam, where is the m factorial?
Yeah, so delta n comma m is 1 only when n and m both are same. So So okay, let me just tell you. So summation over n, suppose you have summation over m equal to 0 to infinity, and then if, okay, and summation over n equal to 0 to infinity, some function f, which is a function of n and m, and then you have delta nm. Okay, so this is equal to, so this particular summation is non-vanishing only when n and m both are same. So m can take values from 0 to infinity, so m will also take value n once. I mean, suppose how do I explain it? So what I mean is delta nm is there, and then this summation m runs from 0 to infinity, and these are dummy variables n and m. So m will also be equal to n at some point. So m equal to 0 to infinity means m will go from 0, then 1, 2, 3, and n, then n plus 1, and so on. But this entire thing will be non-vanishing only when m is equal to n, because of this property of delta function. Delta n comma m equal to 1 if and only if n and m both are same. So we can take this summation over m equal to 0 to infinity and replace, wherever there is m, replace that m by n. So this is equal to n equal to 0 to infinity if n. So the same thing we are doing here. So this is delta m comma n we have. So this left hand side is non-zero only when m and n both are same. So we are taking the summation over m and replacing m by n everywhere. So if I replace m by n in the denominator, I will be left with n factorial times n factorial. So that is n factorial square, and root of that will give us n factorial. And also here it's alpha to the n, alpha star to the power m. So I will get alpha to the power n, alpha star to the power n, but I can write it as alpha star whole to the power n, and alpha star is nothing but mod of alpha square whole to the power n. That's what I have written here. And then I am saying that exponential of x is this, n equal to 0 to infinity. This is because the Taylor expansion of exponential x, you know, that is 1 plus x square over 2 factorial and so on. So that we can write in this form. And so basically this entire thing is giving us exponential of mod of alpha square. So then from there we determine d0. Is this clear?
Yes, ma'am.
Okay. I mean this you could understand what happens, or you already know maybe. I was repeating, I don't know.
Yes, madam.
You okay? That is not necessary. So basically then our coherent state is summation over n, alpha to the power n over square root n factorial, and d0 we have obtained, that is exponential minus mod alpha square over 2 okay, n. Now we will do little more. So n is what? You will get a state having n number of particles starting from the vacuum state if you act with the creation operator n number of times, and then there is that normalization factor. So n particle state you can get by acting with this creation operator on the vacuum state on it by so n particle state you can get from the vacuum state by acting with this creation operator n number of times. you know this, right? Or should I explain this? So one particle state, how do you get? You act with a dagger on 0 ket, correct? And there is that normalization property, that normalization constant. So a dagger on n should be equal to some coefficient n plus 1, because these are creation operators, so they take us to n plus 1 state from n particle state. And then this, I am telling you how we determine that constant Cn. So n a is equal to n plus 1 Cn star, and then if we take inner product of these two, we get n a dagger n Cn mod square n plus 1 n plus 1. Now these are all basis states, so they are orthonormalized, so that is equal to 1, and mod Cn square is n a dagger n ket, and then we know the commutation bracket between the creation and annihilation operator, that is 1. A dagger commutator is 1, so a dagger is nothing but 1 plus a dagger a. So if we replace that, we get mod Cn square 1 plus a dagger a. But what is a dagger a? A dagger a is nothing but the number operator, and number operator, which is a dagger a, when it acts on n particle state, it gives you eigenvalue n ket. So therefore mod Cn square is nothing but 1 plus n, because you will get n inner product, and because those are basis states, those are orthonormalized, that is again 1. So Cn is square root of 1 plus n. Okay, so that's why we say that when a dagger acts on n particle state, it gives you square root n plus 1 ket, meaning a dagger acting on n particle state is equal to 1 plus n plus 1 ket. Now because of this n plus 1 square root coming in, when you act n number of times, you have to divide by n factorial. So one particle state you can get from the ground state by acting with the a dagger operator once. So a dagger acting on 0 will give you square root of 1 plus 0, then 0 plus 1 ket, and that's nothing but 1. Likewise, if you act twice a dagger, if I act again with a dagger on this equation, we get a dagger square on 0, that is a dagger on 1, sorry, these are operators I mean, okay. So a dagger on 1 is what? Square root of 1 plus 1, that's 2, then 1 plus 1, so 2 ket. So likewise, if you act with a dagger once more, so that is square root 2 a dagger acting on 2 particle state, that is square root 2 plus 1, then 2 plus 1 ket, that is 3 ket. So square root of 3 times 2, 3 ket. So you can see the pattern. So if you act n number of times on the ground state, you will get square root of n factorial nth state. That's why I was saying that n particle state is nothing but a dagger, that is creation operator, acting on the vacuum n number of times divided by square root of n factorial. So okay, so this I said because this n particle state is appearing in the coherent state, we can replace this here to write our coherent state as, so alpha, which is equal to 0 to infinity exponential minus mod of alpha square over 2 alpha to the power n over square root n factorial, and then n kth, which we can replace in terms of the vacuum state. Okay, and now, so it doesn't involve n over which our summation runs, so we can take it outside the summation. Okay, now what is this entire thing? This is again another exponential, so let me write it in a better way so that you can understand. It's n equal to 0 to infinity alpha a dagger whole to the power n divided by n factorial on vacuum. So this is nothing but exponential of alpha a dagger. Okay, because I already said in the earlier page, but let me say that again. So exponential x is, Taylor expansion of exponential x is 0 to infinity x to the power n over n factorial. Okay, so that's what we are using here. So this is our coherent state. Now this can be written in more compact way if we introduce another term. We are introducing that term, but that term is actually not changing the state. Why I'm saying that, I'll tell you. So minus alpha star a on 0, but this is actually not changing your coherent state, because this particular portion will still give you vacuum, because what is this? This is 1 minus alpha star a plus alpha star a whole square over 2 factorial plus dot dot dot, and that acting on vacuum. So you know that annihilation operator acting on vacuum always gives you 0. So a on ground state gives you 0. So that's why this entire thing is nothing but your vacuum state or the ground state. So by adding this particular term, we haven't made any changes to this equation, but this is being added just for convenience, just to write this coherent state in a better way. And that better way is as follows. Suppose you have two operators a and b, commutator of which is a constant. Okay, if so, this identity, I mean, ma'am gave during the lecture, you must know it, but let me just say this because I think probably we need it in the assignments. So if the commutator of any two operators, okay, a b, is a constant, then this identity holds that exponential of a plus b is equal to exponential of a exponential of b exponential of half AB commutator. Let me see if I will remove the correct identity. Right. No, wrong. There is a minus here. Okay, so this is the identity. Okay, if A and B commutator is a constant, then this identity holds. This identity, then this identity holds. So okay, so now you can see here we have these three exponentials. Okay, so order of this will not matter because AB commutator is a constant, so you can write it here or here, it doesn't matter. But you should keep in mind that A dagger and A do not commute, so you shouldn't write this particular exponential here because they do not commute. You cannot just switch them back and forth. Okay, so that is one point. And so in this equation then, what is A and B for us? Capital A for us is like alpha A dagger, and capital B is minus alpha star A. So what is the commutator of A and B? It's minus of mod alpha squared A dagger A commutator, and A dagger A commutator is minus 1, so it's mod of alpha squared. So what do you get on the right hand side? You get exactly this three terms, right? When you replace AB commutator by mod of alpha squared, so that will give you this term, and A is this alpha A dagger and B is minus alpha star A. So basically these three terms you can write as exponential of A plus B, alpha minus alpha star A on vacuum. Now this is written as, this nomenclature for this term is like d alpha. This is called displacement operator. It displaces the vacuum state by alpha, so this is called displacement operator.
Madam, can you please explain once again?
Which portion? From where you couldn't follow? You can you tell me?
That is the exponential of AB. That is the portion.
Okay. So this portion, okay. It's very important that you understand this, so that you don't make mistakes. So what happens usually is that, suppose you have two numbers x and y. So exponential x times exponential y, what do? You just add them. You write it as exponential x plus y, right? You do this often while doing math problem or whatever. If you have two numbers x and y, these are just numbers, so they commute. But if you have operators, so here we have operators in the exponent, we can't just write, so it is exponential of three terms, right? Product of three exponentials. So you can't just write exponential of alpha A dagger minus, exponential alpha A dagger minus alpha star A minus mod of alpha square by 2. You can't do this because these operators do not commute. Now, so in order to write it as exponential of sum of terms, we need to exploit this particular identity, and that identity says, let me write it on this side, maybe then it will be easier for you. So if you have product of two exponentials, since this is just a constant, so keep in mind, so AB commutator is just a constant, so it is not an operator. This entire thing is just a number. I can keep it here or there, doesn't matter. But what you should keep in mind is that you can't put exponential of A on this side of exponential B, because they do not commute. Their commutator is a non-vanishing constant. Now the identity is as follows, that exponential A, exponential B is not just exponential A plus B, the usual thing that you do, but there is this additional factor coming due to non-vanishing commutator. Okay, now we have now from what we have here, if we think this particular term alpha A dagger to be A and minus alpha star A to be B, and then take commutator of them, we get alpha mod of alpha squared. So basically I'm saying that, just let me write down, so then exponential of, therefore exponential of alpha A dagger times exponential of minus alpha star A is what? It's exponential of A plus B alpha A dagger minus alpha star A times times exponential of mod of alpha square by 2, but then I can take it to the left, or which implies exponential of minus mod of alpha squared by 2 times this entire factor is equal to this term. Okay, so that's what we are doing. So this entire factor I'm just replacing by this exponential alpha a dagger minus alpha star a. So this is the displacement operator, this is the coherent state, which is this displacement operator acting on the vacuum state.
Madam, exponential minus alpha square by 2, why this 2 factor is coming by 2?
Oh, by 2 is due to this identity. This identity is as follows. There is this by 2. Okay. So this identity is called, you can search on internet if you are interested to see. And if it is not constant, then there are additional terms. BELL, I think. Dorf, DOR. Okay, you can search for it and then see what that identity actually is if you are interested. Okay, fine. So this is all I wanted to talk about for the coherent state. There are many more things that we can say here, but let's proceed with the assignment because it's already 6:45. If time remains, I'll again come back to it and say a few more things. Let me talk about the probability distribution. Okay, so because that will also come in the assignment, so let me just say that. What is the probability of finding n particle or n photons in coherent state? So you can see that coherent state is actually linear superposition of, where is it? So yeah, here. Okay, so there are many equivalent definitions actually. We may need any one of these things. So let me just box it so that I can find out immediately. Okay, that is one, or this one. And okay, now this is what I was searching for. So what I wanted to say is that you can see that coherent state alpha is a linear superposition of n particle states. So I wanted to talk about the probability. What is the probability of finding n photons in the coherent state? So you are in coherent state and then you want to find out what is the probability of finding n photons. Okay, so let's use this particular definition of coherent state. So depending on the question, you have to select which particular form of the coherent state you want to use. These are all equivalent. This is equivalent, this is equivalent to this, and those three are also equivalent to this. So depending on the problem, you should see which particular form of coherent state you want to use. So here we want to talk about probability of finding n photons in the coherent state. So we will use this particular form of the coherent state. 0 to infinity. Let me just copy. Okay, so what is the probability? It's projection of alpha onto n particle state mod square. That's all. I mean, you all know this by now very well. So let's write with some other index so that we don't confuse with some other dummy variable. I mean, m mod square. Now this is equal to summation over m alpha to the power m square root m factorial, so minus mod alpha square, then inner product of n with m, and that is nothing but delta n comma m. These are basis states, orthonormalized. Now summation over m if I take, then what do I get? I will get alpha. N has to be equal to m for this to be non-vanishing. So summation over m, so m should be equal to n, then only this term is non-zero. So that's why we replace m by n and summation is gone. Okay, let me know if this is not clear to you. Square root n factorial exponential minus alpha square over 2 mod square. So square if we do, so we get alpha to the power 2n over n factorial exponential of minus mod of alpha square. Okay, now what is the expectation value of the number operator in coherent state? Number operator, which is a dagger a in coherent state. So this is the probability. Okay, is there any confusion to understand what I mean any of these steps?
No.
Okay, expectation value of a number operator in coherent state. What is that? So alpha n alpha a dagger a alpha. Now what is a on alpha? What is a on alpha? What does it give? Annihilation operator acting on the coherent state.
It is the n minus 1.
No.
Root of
Oh,
n
wait. Sorry. Okay. Okay. You might be using this formula. So if a acts on n, you will get n minus 1. Yeah, that's true. But just very basic thing that we started with. Alpha is the eigenstate of a operator with eigenvalue alpha. So a operating on alpha is what? Alpha ket is what? The very basic thing that we just started with. So a on alpha gives you eigenvalue alpha. But okay, what you are saying is also correct. You are using different definition of the coherent state. Okay, so this is the, if we take conjugate of this, then we get this equation. So therefore expectation value of the number operator with respect to the coherent state is what? Mod of alpha square, alpha with alpha inner product. But coherent states are also normalized. I mean, demanding that normalization of the coherent state, we figured out what D0 is. You remember? So let's call it n bar. So therefore what do we see? probability of finding n particles. So there was that mod. So since alpha are not real, alpha are in general complex, you should better write mod of alpha. So mod of alpha to the power 2n. So mod alpha square is, we see that it's the mean number of expectation value of n, which we denote as n bar. So probability distribution is n bar whole to the power n divided by n.
Madam, where from I get the n bar?
No, that is just a notation. I am denoting this expectation value as n bar because that is, this expectation value is coming out to be mod of alpha square. Now in this probability of getting n photons in the coherent state, you have that mod of alpha square. What I want is just replace that mod of alpha square by some factor. So I can also call it x would be confusing because you also have x operator. So let's call it some r, let's say r. Okay, r is not confusing. No, don't confuse with radial. What can I use? C, D. Q will be confusing. Let's call it n bar only. I mean, you can alpha, beta, gamma. Let's call it delta. Okay, delta is not confusing, I think. So mod of alpha square is delta. So it's like delta to the power n exponential of minus delta. And this is nothing but Poisson distribution. So if you search for Poisson distribution, you will get to see this particular form. So my main point was to tell you that the probability of finding n particles in coherent state satisfies this Poisson distribution. N bar would be a better notation. Let's stick to n bar. Just a notation, nothing else. So n bar actually means the average number of particles that you get by taking expectation value of your number operator with respect to the coherent state. So this is the Poisson distribution. So this is what ma'am actually taught. Ma'am just said at the end of the lecture that the probability actually satisfies Poisson distribution, and here I showed you why it is Poisson distribution and how it is. So
before the Poisson distribution state, madam, where from the n bar we are getting this Poisson distribution? Just 1 minute.
Yes, sorry, say that again.
I am telling that you are having that the n bar as the probability.
N bar is nothing but expectation value of the number operator in coherent state.
Okay.
So that is what n bar is, right? So this is what I am equating to n bar. If this is becoming confusing, you can n bar I am defining, so 3 equal to. So this is this definition. This big thing I am not going to write here. It will be very messy. So that big thing I am calling to be n bar. Is this clear now? Better?
Okay, ma'am.
Yeah. So n bar is mod of alpha square, and n bar is defined to be the expectation value of the number operator in coherent state. And so probability of getting n photons in the coherent state satisfies this Poisson distribution. Okay, so that's all I wanted to say. It's 7 already. So let's begin our assignment. The Hermitian conjugate of operator A is, okay, now you tell me, is this true or false?
False.
What is the Hermitian conjugate of A?
It should be a dagger.
It should be a dagger, right? So it's false. If an operator a dagger whole cube is operated on state n, what will be the eigenvalue Can you do this? So we already know A acting on n gives what? Square root n. We proved it. This factor square root n, how it comes. I think A dagger we proved. Yeah, A dagger we proved actually. We started with this and then showed that Cn is square root n plus 1. But anyway, okay, let me just then tell you how we get A coefficient for A also. So A acting on n is equal to some other coefficient. En n, okay, and sorry, n minus 1. So you understand this starting point, how we are equating A on n to be n minus 1 kit. So this comes from, okay, let me tell you that also. So this comes from that commutator of n with A. Okay, this actually gives you minus A. This you can do, right?
Yes, ma'am.
So n is A dagger A, and you know A dagger commutator is 1. So from there you can derive that n A commutator is minus A. Now n ket is eigenstate of number operator with eigenvalue n. So on this equation, so on this operator equation, if we act on n's ket n, what do we get? We get n A acting on n minus A n operator acting on n, which is equal to minus A so this is minus of n So we can see that A operator acting on n particle state is also an eigenstate of number operator with eigenvalue n minus 1. So this state must be proportional to n minus 1, and we don't know the proportionality constant yet, which we write as En. Okay, and so this is the if we take conjugate of that equation, we get n minus 1 En star, and then take inner product of these two equations. That will give us A dagger A n mod of En square n minus 1 n minus 1. Now this is identity, and this is your number operator. So number operator acting on n ket will give you n. So on left hand side you have n, and right hand side is mod of En square. So from there you get the proportionality constant En to be square root n. So that's how A acting on n particle state gives you square root n minus 1. Is this clear?
Yes, ma'am.
Good. Fine. Now, so you know A acting on n, you also know A dagger acting on n, that's square root n plus 1. Now your task is to tell me what is the eigenvalue if this operator, if A dagger whole cube acts on this state n. Can you do that?
B1 is the correct.
Which one? Which option?
No, madam, 1 minute. Plus 1
I
input.
cannot hear you.
Madam, B.
Option B. So okay, let me just write down what you are getting. So a dagger whole cube acting on state n, you are getting n plus 3 square root of n plus 1 n plus 2, and then what, the kate that you are getting, that is what, is it n minus 1, n plus 1, n minus 3? What are you getting for the kate?
N plus 2.
You are getting n plus 2. Well, you have raised thrice and lowered once, of course, n plus 2. That's correct. Okay, now so which one is the correct option? You are saying B. B is correct, you are saying, right? But actually this is a trick question, in the sense that it is asking, so we know that what we are getting is not an eigenvalue equation. I mean, this operator acting on n is not giving you back n state, right? So it's n plus 1 and then plus some coefficient times n. So I mean, it's trick question. So eigenvalue is actually 0, in the sense that it is not giving you the eigenvalue.
Yes, madam.
You get what I'm saying?
Yes, madam.
Yeah. Anyway, but this is correct. What you have figured out is correct. But just read the question properly and then answer, because you know everything. I mean, fine. I'm just trying to fix that here. Delete this page. Fine. Okay, third question. In the number operator basis, the basis state expansion of the operator is given, where dnm will be what? So this is basically question mark. So for m equal to 3, n equal to 0. So first of all, what is dnm? So again, you take the matrix operator with respect to p and q, n comma m both runs from 0 to infinity, dnm p n m q. Now this is delta p n, this is delta m q. So again, that property that this summation will be non-zero only when m equal to q and n equal to p. Okay, so summation goes away and n has to be replaced with p, m has to be replaced with q. So okay, fine. Now, so these are dummy variables, you can call it dpq, doesn't matter, but the thing you have to calculate is this coefficient when m equal to 3 and n equal to 0. So that means you have to figure out what is m equal to 3 so sorry d0 3. This is what you have to find out. Can you do this and tell me? So now A acts on, instead of n, it's 3 particle state.
Getting 0, madam.
It's 0? I don't think it's 0. No, it's not 0. You are making mistake. Do it again.
It is 1, madam.
No. So the formula, what is the formula? Tell me the formula. A acting on n particle state, what do you get? This formula is what you need to use.
Root n minus 1.
Exactly. Exactly. So let's do it together. So A acting on 3, so A square remains, and A acting on 3 will give you square root 3 to get, and square root 3 I can take out. Then A acting on 2 will give you square root 2 1 ket. Is that correct? Then what? Then A acting on 1 ket will give you square root 1 0 ket.
Yes,
0 0
madam.
inner product is 1, so it's what? Square root of 6.
Yes, madam.
Where you were making mistake? I mean, you should see where you were making mistake, then only you will, right?
That is the, I have not multiplied this factorial, the inner product.
Every time A acts on n particle state, the square root n factor comes in. Whenever you act with A on n particle state, there will be this square root n factor and then n minus 1. So keep in mind this factor, otherwise the answers will come out wrong. Fine. So also tell me what is D. So it's only asking C, but you should also tell me what is D. So expectation value of the ladder operator in this state. So L plus acting on YLM, the formula is L into L plus 1 minus M into M plus 1 YL M plus 1. Correct? So this is what, so you have to find out expectation value of L plus in state psi theta comma phi. The question is clear? Can you do this? You just have to use this particular formula. And then also remember that these spherical harmonics are all orthonormalized, meaning inner product of y10 with y10 will give you 1, and inner product of y10 with any other spherical harmonic will give you 0. So first what you should do is act this ladder operator L plus on this state, and then whatever you get, take inner product of that with this state again, but yeah. You can tell me what you are getting for this part, like L plus acting on the state side. What are you getting? This is equal to what?
The root 2, madam.
Root 2, then
Root 2 y1
comma,
0.
okay. Then
Then 1 0. So it is 1 plus 1 root 2 minus root 2 again root 2. 1 1.
1 1, okay. And for the third term?
Third term I'm getting 2 0 0 means the third term is it is there is no third term.
Right. Now this we need to take inner product with this, right, to find the
Yes.
expectation value. So what will we get? So this term multiplying this term will give you non-zero answer. This term multiplying this term will give you non-zero contribution. So that means this is equal to, so you already have this coefficient, so that is square root 3 over 5, and then this coefficient will get multiplied square root 2 over 5 plus 2 over square root 5 from this coefficient, and here you have square root 3 over 10. So this is what? So this is 2 square root 6 over 5. Is that correct? So what is C and what is D in this expression?
Madam, please explain.
Which one? Which portion? This inner product?
Yes, madam.
So okay, so what I'm saying is that you are taking inner product of this with this to obtain the expectation value. Now these spherical harmonics are all orthonormalized. So when you take inner product, okay, let me write down. So copy paste is equal to the state psi square root 3 over 10 y1 minus 1 theta phi plus square root 2 over 5 y1 0 theta phi plus square root 3 over 10 y1 1 theta phi. This entire state with this state. Okay, so inner product of this term with this term, what will you get? 0, because spherical harmonics are orthonormalized. But inner product of this term with this term will also give you 0, because it's y1 1, it's y1 minus 1. Fine? Fine? Hello?
Yes, ma'am. Yes, ma'am.
Okay, now inner product of this with this will give you square root 3 by 5, this coefficient, times square root 2 by 5. Okay?
Yes.
And inner
Yes.
product of this with this again 0, and then inner product of this with this 0, but inner product of this with this will give you square root 2 over square root 5 from this coefficient and square root 3 over 10 from that coefficient, and then you get this. I think it's clear now.
Yes, madam.
Good. So now the constant C is 2 and constant D is 0. The number state 0 is the ground state of the harmonic oscillator, which is annihilated by this operator. Then the position space wave function is this, where A is normalization constant, B is dimension full constant, what is alpha minus beta. So basically what you have to find out is position space wave function psi 0 of x. Can you do this? Do you understand what the question actually asks and what you have to do? The approach?
Yes, madam.
What do you have to do? Tell me.
The position.
You have to find out the form of the position space wave function for the ground state. For in particle state, we would have denoted it as psi nx, and for ground state, we are denoting it as psi 0x.
So we have to multiply that.
Multiply what?
That means A
Yeah.
with
Yeah.
capital A into the power e to the power x square.
You have to multiply A with psi 0x.
Yes, that is that.
And then
equal to 0.
That's right. That's right. And you have to find out what you are getting for psi 0 of x. So A is given. So you can write A in position basis. So you know what is P in position basis. It's minus I h cross del del x. That you act on psi 0x and equate it to 0 and find out what is psi 0x. So once you know the psi 0x, you can figure out what is alpha and beta from psi 0x and then find out alpha minus beta. So since you have understood what you have to do, can you do it and then tell me? You basically have to solve the differential equation, first order differential equation.
Yes, 1 by b it will multiply and it will get zeros. So
yeah. 1 by b, if you take to the right hand side, it's just 0 multiplied by b, 0. So tell me the form of the differential equation that you are getting. So A acting on psi 0 of x equal to 0 and A is 1 over b x plus I b square over 2h cross p, psi 0 of x equal to 0, but I can write it in position basis. So I p is minus I h cross del del x or x psi 0 of x minus of I square is plus 1, h cross gets cancelled, plus b square over 2 del psi 0 del x equal to 0. So the differential equation that you are getting is minus 2 over b square x psi 0 of x. So you can solve it, right?
Yes, ma'am. There is exponential. So,
Exponential what? Do it. So you need to take psi 0 to the left, and then so it's integration of d psi 0 minus 2 over b square is constant, take outside the integration, x dx integration, which implies ln of psi 0 equal to minus 2 over b square x square over 2 plus some constant, call it ln, some constant, okay, a. So psi 0 of x is equal to a times exponential minus 1 over b square x square. Clear? So what is alpha and what is beta? What is alpha and what is beta? Psi 0 is a exponential minus x to the power alpha. So alpha is 2. Beta is minus 2. So what is alpha minus beta? It's 4. Fine?
yes, ma'am.
No doubt? Fine.
No, ma'am.
Moving on to next one. Consider a correlation function f of t, that is this, with x of t as a position operator in Heisenberg picture. 0 is the ground state of the one-dimensional harmonic oscillator. Then f of t will be proportional to m omega to the power a exponential minus I omega t. And what is that a? So what is, first of all, what is x of t? So this was done in the lecture. I will not repeat it, but I will tell you the final form of x of t. X of t is, so basically you know that x at 0 square root h cross over twice m omega a plus a dagger, and x of t is nothing but time dependent creation annihilation operators, and those a of t and a dagger of t were determined in the lecture. So you may go back, and if there is any doubt you can ask me later. And if you replace that a and a dagger, we obtained this x0 cos omega t plus 1 over m omega p0 sin omega t. So this was x of t. Go back and check if you don't remember. Okay. P cap of t is p0 cos omega t minus m omega x0 sin omega t. Fine. Now you can do, because you know x0 in terms of a dagger, and also p0. P0 is what? P0 is 1 over I square root of m omega h cross over 2 a minus a dagger. Fine. So then, oh, you actually don't need p. Anyway, so f of t is 0 xt x dagger 0 on 0. Okay, so let us do it. So x of 0 is nothing but that operator. So square root, me just copy and paste, and this is constant, so I can keep it outside. 0. Now A acting on vacuum gives 0, so this A dagger when acts on vacuum you will get 1, so this is equal to T A dagger 0, since A on 0 equal to 0. Now A dagger on 0 is what? It's A dagger on n is square root n plus 1 ket. So 0 x t 1. Fine. Now x of t we will substitute. Actually, I mean, this problem you don't have to even solve, because A will turn out to be -2, and that you can see because there are two x operators which are multiplying. Which problem is it? Sorry, A will actually become -1. Why am I saying that? Because it is multiplying these two x cap operators. So when you multiply x twice, you will get this coefficient 2 times, right? So that is basically h cross over twice m omega. So the question is only asking you what is m omega to the power this power a. So you can, just by knowing the expression of x, you can say that a will be -1. But anyway, let's solve it. You get my point, what I was trying to say?
Madam, -2 or -1, but
-1 will be because this is square root, right? If you multiply twice, it will be just h cross over 2m omega, and so it's asking m omega to the power what? So m omega to the power -1.
Okay, madam.
Let me just do it. So xt is this. Copy, paste on state 1. Okay, now x of 0 we need to replace, so let's write it. Omega 0 1 cos omega t plus 1 over m omega 0 1 sin omega t. Okay, now h cross over twice m omega, x of 0 is square root h cross over 2m omega 0 a plus a dagger 1 cos omega t, and plus 1 over m omega. T is what was the expression of P? Square root m omega h cross over 2 0 a minus a dagger 1 sin omega t. Now when a dagger will act on this 1, it will give you ket 2, square root 2 ket 2 you will get, but inner product of ket 2 with this 0 will actually give you 0, right? Because these are all normalized, so you get 1 only when n hits n. So basically you will get h cross over 2m omega 0 a acting on 1 cos omega t. Okay, and for this again, when a dagger hits 1, it gives you square root 2 ket, but 2 ket with 0 will again give you 0, so we are not worried about that, and we will just write. So this coefficient I have taken common, these two coefficients, and that gives h cross over 2m omega, and from the second term you get 0 a acting on 1 sin omega t. Oh sorry, there was one I, 1 over I. Expression of p has I, so 1 over I, or yeah, so 1 over I. Okay, this is h cross over 2m omega, and this will give you 1, because a acting on 1 will give you square root 1 0, and 0 0 inner product is again 1, so you will get cos omega t minus I sin omega t. 1 over I is minus I, so h cross over 2m omega exponential minus I omega t, so that form you get exponential minus I omega t, and it is saying proportional to, so they are not worried about these factors of 2 and h cross, and a is nothing but minus 1. Clear?
Yes, madam. Is there minus 2 omega or 2m omega is there? No, madam. Oh, okay.
Yeah, but it is saying
So-
proportional to. It is saying proportional to. So h cross and 2, those are just constants. It's just asking you what is the proportionality factor of m omega, and that's 1 over m omega.
Okay.
The quantity will be what? This quantity. Okay, so here again you need to use one identity. You need to know this. So exponential of x y.
This is a dagger plus a star d one is correct.
Yes. So you know this identity. You have solved it.
Yes, I know this. Please solve it, madam.
Plus what was the identity? Plus 1 over 2 factorial x xy plus dot. So that is all we will need.
So what is the name of this identity, madam? This is the Hausdorff identity?
I think so. This is a different form of that same identity. No, probably. I mean, using that formula only you can derive this. I don't know how to derive it. Because it has similar structure of that. But I don't. But these two are not same. Before the identity that we were using first, that is different from this one. That was just exponential a, exponential b. But now we have another operator y. I don't know what this identity is called. You can check. Okay, so see, in this problem you have this displacement operator, so that's why that displacement operator discussion was important. So you know what the displacement operator is now. That is this particular thing. I'll just copy. So this is equal to d of alpha. Fine. Now, and d dagger alpha is just exponential of alpha star a minus alpha a dagger. So when we do d dagger a dagger d, we basically have exponential of alpha star a minus alpha a dagger, and then exponential minus that same thing, alpha star a minus alpha a dagger. Okay, so what is it? It's y, and for us y is a dagger plus the commutator alpha x with y commutator. That means commutator of alpha star a minus alpha A dagger with A dagger. Now you see that this commutator will give you a constant, and what is that constant? Only this part will survive. A dagger with A commutator anyway trivially 0. So you will get alpha star, and that's why you don't need to worry about these things, because now if you want to take commutator of x, which is this, with xy commutator, which is basically alpha star, you will get 0. So all these terms are actually 0. So that is all, plus you will get 0. So it's plus alpha star. Fine. And so
Madam, can you explain why other terms are 0? Just
yes. So what I'm saying is that xy commutator is coming out to be a constant. So x is this entire thing is x, and this is y, and xy commutator is nothing but alpha star. That you agree? That you agree? This commutator is alpha star, you agree?
yes, ma'am.
So it's a constant, it's not an operator. Now if you take commutator of x with alpha star, what will you get? You will get 0, right? Because it's just a constant, it's not an operator. So it
Yes,
will
ma'am.
trivially commute. So that's why, I mean, the other terms are again nested commutator. So there is some number, then commutator of x with x with x with y, and so on. So all of those will vanish once you have constant xy commutator. So you know this. So now you should also verify that d dagger A d will give you A plus alpha. Okay, this you just do as homework. Fine. Or minus will be there. Okay, so what will happen if it is A? So just this will get replaced by A, and then this commutator will give you a non-zero result, and there is minus already, and A dagger with A commutator is -1, so you will get plus alpha. Simply just do this for your own benefits. The displacement operator d alpha is unitary. Is it true or false?
True.
That's right. I don't need to explain it, because d dagger you can see already, it's just this thing, and so when you multiply these two, now it is again exponential A times exponential B. So when you do d dagger d, you will get exponential of something, exponential something, but that something is nothing but same, right, apart from a minus sign. So that's why you can write that something plus the other thing, and you will get exponential 0, or that is nothing but 1. If two, we have seen, right, if there are two operators which are different, and then we have to worry about the commutator, if it is constant, or if it is 0, then fine, we can write it as exponential of this plus this. But if it is non-zero, then we also get another contribution coming from the commutator of these two operators. I mean, you should keep this in mind. Here it doesn't matter, because the operator inside the exponent is nothing but same apart from a minus sign. So they trivially commute, and you get d dagger d to be 1. Consider a coherent state that is an eigenstate of annihilation operator such that A on alpha is alpha alpha. The probability Pn of finding the state alpha in the number state n equal to 2. So see, we have already discussed this. What is the probability of getting n particle state? So let me copy that. So let me just tell you again. So Pn is nothing but this inner product mod square, and if you do that, you will get this. So I'll copy this particular formula. Where is it? What question? 9. So this is probability for n particle state. Now this question is specifically asking you n equal to 2. So you can see it's alpha to the power 4 over 2 factorial exponential minus alpha square. So question is asking what is q. So q is 2. Correct? Is this fine?
Yes, madam. Yes, madam.
So question 10, it's saying consider a one-dimensional simple harmonic oscillator. Using the number basis, construct a linear combination of 0 and 1 such that the expectation value of the position operator is as large as possible. So among these states, 4 states, so you have to find out expectation value of x such that this is maximum. For which particular combination the expectation value will be maximum is what the question is asking you. So
The answer is B, madam.
yeah, so you have solved it. This was there in the assignment, current year assignment.
It was there, but please solve it again, madam. I am a little bit confused. I just guessed that one.
How did you guess it? I mean, what was the thought process? You can tell me. Just like how did you guess it? Then we can see if it was correct or wrong.
What is this? The expectation value of the position operator rates.
So let's call that state psi square root 0 plus 1. So expectation value means you have to basically calculate this. Now x operator for a one-dimensional harmonic oscillator is h cross over 2m omega a plus a dagger. Now okay, now one reason for not choosing anything between a and d is that these two are not normalized, first of all, but other than that, the denominator is, I mean, denominator should have been, if the denominator was square root 2, then these two states were also normalized, but
Yes, but that is the reason I cancel it, and I saw the C1 is having I. So that is why I cancelled that one. That is the thought process.
no, but C is, I think, normalized, isn't it?
Yes, it is normalized.
Yeah.
The I state, there is a one.
Yeah, but if you calculate expectation value of x with respect to this particular state, you will get 0, and expectation value of x with respect to this state will come out to be 1.
Okay, madam, please can you solve anyone?
So this will be half 0 plus 1 acting on x cap a plus a dagger 0 plus 1, okay, half square root h cross over 2m omega, then inner product of 0 plus 1. Okay, so let's keep the dual vector as it is, and we want to act this operator on this state. So what happens when A hits 0 ket, it gives 0. When A hits 1, it gives square root 1, 0. So you get 0, and then plus when A dagger hits 0, it gives you square root n plus 1, that means 1 ket. When A dagger hits 1, it gives you square root of 2 ket. Now you take inner product. So this inner product will give you identity, and this inner product will give you identity. So 2 square root h cross over 2m omega half 1 plus 1. So you get square root h cross over 2m omega. I mean, if this constant is 1, then you will get 1, but but anyway, you get this, and for this if you solve you will get 0. You can check that. Fine. You will basically get 1 minus 1 here, so that will give you 0. Okay, this last question I want you to do as homework. I mean, you can do this, right? You know all the formulas now, so you can just do it to get your hands on it. So you can write x in terms of a dagger, p in terms of a dagger, and trick is that whenever you have equal number of creation and annihilation operator, then only this kind of expectation values give non-zero value, otherwise it gives 0. But you can just do it for your own benefits.
Which one you means equal number of annihilation value operator? That means A has equal number of annihilation operator, madam.
So if you have a dagger acting on n, you get non-zero value, right? You don't get 0. But if you have suppose a square, so a dagger on a will give you some constant times n plus 1. Then a square will give you n. Then a on n will give you n minus 1. Now if you take inner product of n minus 1 with n, you get 0, right? So, so this is what I meant to say. If you have same state on both sides, and your creation and annihilation operator, number of creation and annihilation operators are same, then you get non-zero value, otherwise you will get 0. So just do it, these 5 matrix elements, okay? And if any problem you face, then you can tell me in the next session.
Okay.
Cool. So let's stop here then. See you next week. Fine?
Okay, madam.
Yeah, bye bye.